Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week we continue our industrial AI series with Sergey Levine, an assistant professor at UC Berkeley whose research focus is deep robotic learning. Sergey is part of the same research team as a couple of our previous guests in this series, Chelsea, Finn, and Pieter Abbeel. And if the response we've seen to those shows is any indication, you're going to love this episode. Sergey's research interests and our discussion focus in on how robotic learning techniques can be used to allow machines to autonomously acquire complex behavioral skills. We really dig into some of the details of how this is done, and I found that my conversation with Sergey filled in a lot of gaps for me from the interviews with Pieter and Chelsea. By the way, this is definitely a Nerd Alert episode. Before we jump into the show, I'd like to thank everyone who's taken the time to enter our AI conference giveaway. You all know that one of my favorite things to do is to give away free stuff to listeners, and we've been fortunate to be able to give away tickets to the O'Reilly AI conference to lucky TWiML listeners since the very first event in the series last year. Well, we've got a couple of exciting updates for those of you who want in on this opportunity. First, we're making it even easier to enter our ticket giveaway for the San Francisco event. And second, we're giving away 2 tickets now, not just one. To enter the contest in 30 seconds or less, just hit pause right now and visit twimlai.com/AISF right from your phone. Finally, a quick thank you to our sponsors for the Industrial AI series, Bonsai and Wise.io at GE Digital. By now you know a bit about Bonsai, right? You've heard me mention their AI platform, which lets enterprises build and deploy intelligent systems. Well, I actually spent some time in the Bonsai offices in Berkeley last week, learning more about that platform and recording an interview with their co-founder and CEO, Mark Hammond. It was a great conversation, and I'm really looking forward to getting it up on the podcast in a few weeks. In the meantime, I'll reiterate that if you're trying to build AI-powered applications focused on optimizing and controlling the physical systems in your enterprise, whether robots or HVAC systems or supply chains, you should take a look at what they're up to. They've got a unique approach to building AI models that lets you model the real-world concepts in your application, automatically generate, train, and evaluate low-level models for your project using technologies like reinforcement learning, and easily integrate those models into your applications and systems using APIs. You can check them out at bonds.ai/TWiMLAI and definitely let them know you appreciate their support of the podcast and this series. Last week, I announced Wise.io at GE Digital as a sponsor for this series as well. Wise.io was among the first companies I began following in what I call the machine learning platform space back in 2012-2013. I've since interviewed co-founder Josh Bloom here on the show and mentioned the company's subsequent acquisition by GE Digital. At GE Digital, the Wise.io team is focused on creating technology and solutions that enable advanced capabilities for the industrial Internet of Things, making infrastructure more intelligent and advancing the industries critical to the world we live in. I want to give a hearty thanks and shout out to the team at Wise.io at GE Digital for supporting my industrial AI research and this podcast series. Of course, you can check them out at Wise.io. And now, on to the show. Hey everyone, I am on the line with Sergey Levine. Sergey is an assistant professor at UC Berkeley in the EECS department, and I'm super excited to have him on the show. Hi, Sergey.
Hello.
How are you doing?
I'm doing well.
Wonderful, wonderful. How about we start by having you introduce yourself and talk a little bit about your background and how you got interested in your current area of research and what that is.
Sure. So I actually started off in graduate school working on computer graphics, and particularly in computer graphics, I was really interested in simulating virtual humans, simulating virtual characters. And the trouble is that if you want to simulate very realistic virtual humans, one of the things you have to do is you have to simulate intelligence, because humans are intelligent and machines by default aren't. So a lot of my work turned out to be essentially artificial intelligence work in computer graphics to get these virtual characters to behave in ways that look plausible. So from there, I decided that, well, if I have some methods that work reasonably well in computer graphics, I can create some plausibly realistic virtual humans. Perhaps those are methods that are also applicable, for example, to robotics. So I did a postdoc after that in robotics. It turns out that a lot of this stuff works well for robots as well. And a lot of that led to my current work in reinforcement learning and deep learning.
Fantastic. I noticed on your website that you've got a paper accepted, or you're speaking at a computer animation conference. Are you still fairly active in the video domain?
Not as much in recent years. So I think my last paper there was in 2012. I am giving a guest lecture this summer actually at SCA, that's a symposium on computer animation, to talk about some of the recent progress in deep reinforcement learning. So actually, since I moved to robotics, actually a lot of this technology has made actually a big impact in graphics, and that's really right about now in this past year that's been registering a lot. So they invited me to come give a talk to them about how some of this stuff is going.
Fantastic. Fantastic. So as you know, we recently had on the show Pieter Abbeel and Chelsea Finn, who are your colleagues there at Berkeley. And the conversations I had with those guys were really, really interesting. And let's maybe take a minute to talk about the research that you're doing in a little bit more detail, and we can dive in deeper.
Sure. So the area that I work in can be broadly categorized as robotic learning. So I'm interested in developing algorithms and models that can allow robots to autonomously learn very large and complex repertoires of behaviors so that they can take on more and more of the functionality that we associate with intelligent human beings, so that they can do all the things that are dangerous, unpleasant, or for other reasons undesirable for people to do themselves. And to me, this problem is not just a problem that has a lot of interesting practical implications, it's also something that I think can serve as a really valuable lens on artificial intelligence, because in the end, we have only one proof of existence of true intelligence, that's human beings, and human beings are embodied. So we don't just exist sort of in the ether thinking abstract thoughts, we actually have a body, we interact with the world, and the nature of that interaction is very central to shaping who we are and how we reason about things. So I think that dealing with systems that are embodied, systems like robots, give us a very valuable perspective in understanding how we might be able to construct artificial intelligence.
So more so than some of the non-physical applications of machine learning and AI, including other deep learning applications like gameplay.
Well, so the thing about other applications of AI is that oftentimes, especially in things like computer vision, speech recognition, and so on, we work with just the perception half of the equation. So we think about how we can take in data and produce a particular answer. The nature of intelligence is much more complex than that. It's about taking in information, reasoning about it, making decisions, thinking about the outcomes of those decisions, and so on and so on. Now, you mentioned game playing, which has some elements of this, but one thing that game playing won't let you do is it won't let you tackle the full complexity and diversity of the real world, because the real world is characterized not just by its sequential nature, but also by its diversity, by the sheer number of unexpected things that might happen in a natural interaction, which computer vision has dealt with for decades, but without handling the decision-making, and the game playing handles the decision-making, but without handling so much of the diversity.
So to what degree is your research in robotic learning kind of integrative across all these different fields? Are you specifically focused on pulling together, some of the state-of-the-art research from these various fields, or is your domain within robotic learning kind of established and you're heading down a path that way? I don't know if that question makes any sense, but if you kind of get a sense from where I'm going.
I think I see where you're going. This is actually a very good question, and it's something that for robotics has been sort of one of these big tensions over the years, is that it's often been very tempting for researchers to think of robotics as fundamentally a systems or integration exercise. So if you have, let's say, a very effective computer vision system and you have a very effective, let's say, planning system, well, maybe building an intelligent robot is just a matter of welding those pieces together, connecting up the wires and seeing it work. And a lot of people have hoped for exactly this, that by making progress independently in different domains, we'll get closer and closer to intelligent robots. Unfortunately, reality hasn't quite panned out that way. And a lot of roboticists will actually lament that if they take sort of the latest ImageNet trained model and put it on their robot and try to use it for object detection in the wild, it'll actually do a pretty terrible job because the biases that are present in the kind of data sets that those models are trained on don't really reflect what a robot will see from its cameras in natural environments. So I actually think that in order to really get this right, we need to draw on the lessons in the state-of-the-art models in, game playing, vision, and so on. But at some point, we have to kind of do a lot of that ourselves. We have to take the lessons, but not necessarily the technical components themselves. And for that reason, I've actually been a really big advocate of end-to-end training for robotic learning, where we set up models that include both perception and control and actually train them together to perform the particular tasks the robot needs to handle, instead of relying on integration of existing components.
In taking a look at your research, I came across a really interesting example of the effect you're describing. The particular research was where you were training a robot arm, I think it was a Baxter robot, to tie knots in a rope. And some of the comments associated with the research on I think there was a GitHub page about it, was that, hey, we trained this system on I think it was a red rope, and we're working hard to make it work with a white rope also that's a little bit stiffer. And we trained it on a background that was a green background, and we found that doesn't generalize to other backgrounds. Mm-hmm. This is a conversation point that came up with Pieter as well, this notion of mastery versus generalization. Mm-hmm. Can you talk a little bit about that and how your research is taking that issue on?
Yeah, absolutely. So the Baxter paper that you're referring to there, what we did is we actually had a robot practice tying knots, but of course it was one robot and it was practicing tying knots in one particular rope. So the resulting system could do really well at tying knots in that rope. It could kind of tie knots in ropes that looked a little similar, and it pretty much broke down if you gave it something, a rope that was too thick or too thin or something like that. Mm-hmm. But here's the thing, that in robotics, there's oftentimes when we run experiments, the experiment is the entirety of the data collection process. So if you imagine an experiment in computer vision, you take all of ImageNet, you train your model on it, and you show its performance. In robotics, an experiment basically amounts to generating an entire new data set, training your model on it, and then observing its performance. So of course, if you're generating an entire data set every time, if you have one robot, just a little bit of time, it's not going to generalize very far. We did actually try to study at one point what would happen if we scaled up this style of technique. We did this actually in partnership with Google, which has quite a bit more resources as far as deploying large numbers of robots. And we tried to see actually, if we run data collection at the scale of something like ImageNet, can we actually get robotic skills that generalize effectively? Mm-hmm. So what we did there is we set up, we call this the ARM farm by analogy to server farm. We set up a cluster of about 14 robots, and we had them basically working day and night to practice grasping objects. So we chose grasping because it's something you can do to pretty much any object, and it's also very important for a lot of other robotic manipulation tasks. And we had them running day and night like this, and they collected about 800,000 grasps. Each grasp had maybe 5 to 10 images, so the total size of the data set was about in the same order of magnitude as ImageNet. And there we did find that actually the resulting networks that you train on that really large data set, they do actually generalize effectively to new objects that are completely different than what they've seen before. In fact, when you do learning at this larger scale, you can observe some really interesting emergent behavior. One of the things that we were thinking as we did this work is, grasping is a very geometric behavior, so probably the first thing that these systems will learn about is the geometry of objects in the world. So they'll learn that, you need to put the finger on one side, put the finger on the other side, and so on. What we saw, which surprised us a little bit, is that in the earlier stages of training, when you have maybe 100,000 grasps before we collected the full data set of 1 million, in the early stages of training, the network actually didn't pay as much attention to geometry, but what it did do is it paid a lot of attention to material properties. It recognized right away that if something was really soft, then it could pinch it and pick it up really easily. But if something was rigid, then it couldn't do that. And this is completely different from how conventional manually designed grasping systems tend to work, because when you manually design a grasping system, you're going to use some sort of geometric motion planning, and you're going to completely ignore the material properties. So that was really, really interesting to us. And that sort of underscored, I think, the value that you get from using learning through trial and error, because you actually learn about the patterns that are really present in the world rather than the ones that your analytic model thinks are important.
Are there any other emergent behaviors that you observed in that set of experiments?
Let me see. So that was the only one that we could pin down in the sense that we could actually measure it. Like we could actually put different objects in front of it and quantify that. Yes, it was really employing this strategy. Informally, there were a few things that it did tend to do pretty consistently that I can kind of speculate a little bit about. I just don't have the hard numbers for it. It tended to figure out, for example, that if you have something like a brush, that you should pick up the brush by the stiff part rather than the flexible bristles, which is nice. It tended to figure out that center of masses of objects really matter, especially for awkwardly shaped objects. So those were some of the things that it picked up on. There were also a few mistakes that it actually made that were kind of amusing. So it just so happened that a lot of the soft things in our training objects were brightly colored because we wanted to buy small items of clothing, and small items of clothing are children's clothing. And children's clothing tends to be brightly colored. So it had this association of things that were brightly colored were soft. And in our test set of objects, we had a pink stapler. And that pink stapler was just impossible for it to pick up because it was just convinced that this pink stapler was a soft, fuzzy thing and it could just pinch it. So that's a good example, actually, of the kind of funny dataset biases that you can get that will actually affect you even in real-world tasks like this.
Interesting. When I hear you describe the examples, an example like the pink stapler, it makes me wonder, to what extent is it possible to layer the traditional object recognition types of technologies into a model like this? Like, should it be able to recognize the stapler first and then have some higher level abstraction that we're also training on in addition to just the raw pixels? Is that something you looked at?
Yeah, that's a very good question. That's actually something that we've thought about a lot here. So one of the big things that you get out of traditional approaches to object detection, it's not actually the models themselves, it's the data. There's very large and extremely diverse data sets, labeled data sets of objects with bounding boxes, segmentation, and so on. And it would be really nice to try to use that. But at the same time, you want to avoid losing the benefit of end-to-end training. So if you simply run a bounding box detector on what the robot is seeing and then ask it to pick things up, well, it's not just the bounding box that matters for the grasp. It has to also understand something about what's in that bounding box. So you don't want to lose the benefit of the end-to-end training, but at the same time, you want to somehow get more out of all these auxiliary sources of information. One of the things that we've been working on a little bit, and this isn't out yet, but this will be released in probably a couple of weeks, is some work on semi-supervised learning of robotic skills, where we combine experience from the robot's point of view that includes the actions that it took and the observations that it saw with kind of a weakly labeled image data set. And weakly labeled in the sense that that data set just tells you, does the image contain the object that the robot needs to use? So if the robot is learning, for example, how to put a cap on a bottle, the weak labels might say, does this image contain a bottle or not? And the idea is that the robot itself, when it's interacting with the world, maybe it only gets to interact with a few instances of those objects. So it can use those few instances to understand the physics of the behavior, but it's not really enough for it to really generalize to understand what the entire class of objects of this type looks like. So the weakly labeled data is there to basically show it, what can this skill be applied to? And the important thing when incorporating this weakly labeled data is not to lose the benefit of the end-to-end training. So in this technique that we developed, we're actually including the weakly labeled data and the robot's own experience at the same time in a joint training procedure, rather than actually splitting things up into components and then trying to wire them up together as in the more kind of conventional systems approach. And that turns out to work very well. Under the hood, the method has kind of an attentional flavor to it. So it basically learns what kind of objects to pay attention to from the weakly labeled data and then uses that attentional mechanism to actually perform the task when at test time.
How do you express weakness in this model?
Well, when I say weakly labeled, I just mean that the images have a label that only tells you whether the object you care about is present or not. So, you can think of it as a person telling the robot, here are the things that you can execute this skill on. So here are lots of pictures of the thing that you can do this task to, and here are all the pictures of things that you cannot do this task to.
Right. And is there a general approach to incorporating in kind of higher level abstractions into models like this? Meaning, in the case of going back to the stapler example, we could do the object detection and determine that, hey, this is a stapler, but there's also, there are other neural nets or other examples that can do geometry detection and things like that and orientation detection. And I guess the question that I'm trying to get at is, it sounds like the general approach to applying deep learning in this model is, let's just collect a bunch of data and, throw it at and train on a bunch of data. And if there are important features, the model will figure it out. The network will figure it out. And what I'm curious about is that I guess what are is there an analytical foundation to that assertion? And if not, are there other ways that folks are looking at incorporating in abstractions or features into, these models to help them, both generalize and train faster?
So I think there's perhaps a little more to it than that. So it used to be that when we thought about kind of the previous generation of machine learning models, the way that we would imagine using them is exactly what you described. That we'd say, okay, we have some edge detector, we have a pose detector, we have some kind of thing that will analyze local geometry, we'll plug that into the downstream module, and so on and so on. The thing about deep learning is that the model itself, it's good for making predictions, but there's nothing kind of unique or special about it. You can actually have the same model perform multiple tasks, and that's often not actually that much harder than stapling together two models that each perform those tasks. So if you want a model that can, segment an image and detect poses of objects, you could train two separate models and then combine their outputs, or you can just train one model that does both of those tasks. And the latter is often not actually that much harder. But it has a substantial benefit, which is that when you train a single model to perform multiple tasks, it can actually learn internal representations that share the knowledge that's contained in those two tasks. So if you were to ask me how I would consider combining, let's say, a object pose detector and a grasping system, I would much rather train a single model that predicts both pose and grasp than to take a pose predictor and feed its output into a grasp predictor. And the reason for that is that the data already has all the information. There's nothing, magical that's contained in the model that's not already contained in the data. And It's possible to train these joint models. So I might as well take both data sets and train one model that'll benefit from the shared structure in both of those tasks than to train two completely disjoint models and then try to staple them together afterwards.
Right. Have you run into situations where there are pre-existing models trained on inaccessible data? I guess I'm kind of chasing the tail of the scenario a little bit, but it sounds like, there may be some corner case where it makes sense to do that if you don't have access to the data, but you do have access to the model. But I get the point that in general, the data is the data. And if you can train one model that can build these internal representations, it's much more efficient than trying to engineer one model that can solve part of the problem and another model that uses that to solve the thing that you're actually trying to do.
Yeah, basically, it's a lot easier for us to compose data sets than it is to compose models.
Right. So one of the challenges that comes up that you've spent some time looking at is the efficiency of training these deep learning models. Sample efficiency in particular is one of the ways you talk about that. Can you talk a little bit about that problem and the things you've done there?
Right. So I assume you're referring specifically to sample efficiency for deep reinforcement learning algorithms.
That's correct.
So deep reinforcement learning algorithms are kind of a funny creature. Deep learning, like standard deep learning with gradient descent, it's a common perception that it's inefficient. And in some sense it is. Like, we can build very good object detectors, but we need maybe millions of images to train them, which might seem like a lot. But, if you consider what that model is really doing, it's reasoning about pixels, edges, everything from those pixels and edges all the way to complex higher level concepts. That's actually pretty sophisticated. With deep reinforcement learning, though, things get a lot worse. So if you look at the kind of sample complexity for learning to play, let's say, a simple video game like Pong, there you're going to be looking at, millions or even tens of millions of images for a task with visual diversity that's nowhere near what we see in conventional, let's say, computer vision data sets. So visually it's very simple, physically it's very simple, but you need a lot of samples to learn that task, and those samples involve actively interacting with an environment. Now, it happens to be a simulated environment, so you can run it much faster than real time on a server, but still something here seems a little out of whack. Something here is a lot worse than perhaps it should be.
And what's the intuition for why that is the case?
There are a couple of reasons for it. The short version is that we don't fully understand, but the long version is that there are a few things that are being done that could perhaps be done differently. Now, if I knew exactly the answer to this, then of course I would have a much more efficient algorithm to give you. But it's possible to guess a few things here. One of the things is that reinforcement learning provides a much weaker signal than supervised learning. So in reinforcement learning, even though it's gradient-based optimization, you don't really have gradients of the thing that you really care about. You're sort of estimating them in this very peculiar way, depending on the reinforcement learning algorithm that you use. So you essentially get a lot less information from every gradient step. A lot of reinforcement learning algorithms also tightly couple the collection of data in the environment and the updating of the model, which is very different from supervised learning. So in supervised learning, you first collect a large data set, and then you take many, many gradient steps on that large data set. In reinforcement learning, you often interleave collection of data and updating the model because you need to collect data that agrees with your model. So if you're learning a policy, you'd like to collect the kind of experience that policy will actually see, and you want to do this iteratively. So that means that you're often throwing out lots of data from old policies that you can no longer use because your policy has changed. And that prevents you from reusing old data. So that can be very harmful for sample efficiency. In fact, some of the most inefficient methods like policy gradient, that are very convenient to use in simulation, they're often the most inefficient in the real world because they can't reuse data. So we need to look at methods that can reuse old data. These are sometimes called off-policy algorithms.
Before we go there, can you elaborate on the throwing out of the data? Is this something that the algorithm is doing as part of the way it's constructed, or is this something that we're doing manually? Tell us a little bit more about what we mean by that.
Oh, so that's just how a lot of on-policy, policy gradient algorithms work. So these algorithms will operate as following. They will collect experience from the current policy. They will compute a gradient descent direction on that experience. They will take that gradient step, update the policy, and now they need more data from the latest policy, which has now been updated. So they have to throw out all the old data and collect a new batch of data. So you can kind of, if you want a mental picture of what this looks like, if you have a robot that let's say is learning to walk, it'll try to walk a couple of times, update its behavior, try to walk a couple more times, and so on and so on. And that's the reinforcement learning process. But you have to remember that each time it changes behavior like that, it has to basically collect new experience because it needs to understand how well its current policy is really doing.
Right.
So that can get really, really expensive in terms of the amount of time it needs to spend collecting experience. So if you're running stuff in a simulator on a server farm somewhere, then it's okay. You can parallelize all that and everything is reasonable. But if that's a real physical system that's actually executing those trials, that can get extremely time consuming.
Okay, and you were about to talk about some of the ways we can get beyond this.
Right. So one of the things we can do is we can look at off-policy algorithms. So these are algorithms that can supplement their training with data from other policies. So what can you learn from other policies? Well, intuitively, one of the things that you can learn is you can learn about predicting future events. Because, the rules of physics and so on, they will hold true regardless of which policy you're executing. And the kind of future events that you can predict can range all the way from very detailed, where you're actually predicting, let's say, the entirety of your future observations, and this is sometimes called model-based reinforcement learning, or all the way to something fairly abstract like the future rewards that you will see. And this is actually a type of model-free reinforcement learning that's sometimes referred to as value function estimation or Q-learning, that also falls into this category. But they're all kind of prediction-style methods. So on the one extreme, you're predicting the entirety of your future sensory observations, and on the other extreme, you're predicting something very abstract like rewards that you will see in the future. And that tends to be more efficient because that allows you to incorporate data from other policies, including your own past policies.
And so can you talk a little bit about those policies and how they differ from one another?
Yeah, so I can talk a little bit about the model-based reinforcement learning because I feel like this is something that perhaps hasn't gotten quite as much attention in the research community in recent years because there's been a lot of excitement about model-free reinforcement learning. The model-based reinforcement learning is perhaps not as far along because the prediction problem that it's trying to solve is a lot harder, but it has a lot of promise for dramatically improving sample efficiency for two reasons. The first reason is the one I mentioned, that you can use data from other policies. But the second reason, which is perhaps a little more subtle, is that in model-based reinforcement learning, every sample has a lot more bits of supervision. So if you imagine what you're doing when you're, let's say, predicting a value function, you're predicting one scalar value that's a function of your current observation or state. When you're predicting everything that will happen in the future, maybe you're predicting future images that you will see, there are many more bits of supervision in that prediction problem. So every single sample actually carries a lot more bits of supervision, and that means that your model can learn a lot more from each of those samples. Now, the flip side of the coin is that your model is now trying to solve a much harder problem. It doesn't have to predict just a single scalar value, it has to predict an entire image. So it's sort of a little bit unclear how that shakes out, but potentially the benefit in sample complexity can actually be quite substantial there. We've done a little bit of work on model-based reinforcement learning for vision-based tasks, actually on real physical robots, and this is some work that we did that also involved actually parallelizing data collection across multiple robots, but at a much smaller scale. So with the grasping, I mentioned that we needed about 800,000 grasp attempts. For the model-based reinforcement learning, we actually trained a video prediction model for pushing objects around on a table with about 50,000 pushes. And that was actually effective for generalizing to new objects and pushing them in new directions and so on, simply by predicting what the robot will see in the future and then taking the actions for which that model predicts the kind of outcomes that you want. So that was already a lot more efficient, and it ran on real physical systems. Now, the downside is that because the prediction problem there is so hard, the predictions were very short range. So the robot could only execute behaviors maybe with a horizon of 2 to 3 seconds. So these weren't very complex behaviors. And that's because the prediction problem is so hard. But hopefully, as we get better and better video prediction models, which is a very active area of research right now, these methods will get better and better.
Is that the inverse reinforcement learning problem?
No, this is the model-based reinforcement learning problem.
So when I looked at again, going back to the Baxter robot video, it talked a little bit about this inverse RL where it sounded like you're doing the same thing. You've got your rope in one state, you have the human move it to another state, and then you're looking at the robot action that it would take to get it from one state to another and producing the inverse of that. Or that becomes the action that the robot takes to move the rope to a position that's required to imitate what the human did. So that's the inverse RL. What you just described sounded very similar to that.
So I think what you mean is actually inverse dynamics.
Dynamics, okay.
So when you have a model-based reinforcement learning problem, there's actually different ways that you can represent your predictive model. The most common way is to build what's called a forward dynamics model. So forward dynamics means that you're predicting from the present to the future. So you're looking at your current observation, your current action, and you're predicting what the next observation will look like. Inverse dynamics means you're predicting from the future to the action. So that means that you're looking at your current observation, your future observation, and you're predicting what action will get you from one to the other.
Right. So I've got the rope in position A, I've got the rope in position B. What's the action that's required to get it from A to B?
Exactly. So it's just another kind of predictive model, and they have different pros and cons. So with a forward model, you can run it forward many steps because you can basically recursively apply it to its own predictions, but you have to work a little harder to get the action. With the inverse model, the action comes right out of the model, but it's difficult to chain it together because you don't know what the following observation will be, because the model doesn't predict observations, it predicts actions. So inverse models are perhaps a little easier to use, they're a little easier to train, but they're a little harder to use for longer term planning.
Okay. So in the discussion about sample efficiency, one of the things that I came across was mirror descent guided policy search. Can you talk a little bit about that and where that fits in?
Sure. So mirror descent guided policy search is a technique for optimizing very complex policies, like deep neural network policies, by only using supervised learning to train the policy itself. And that sounds a little bit funny because if we're doing reinforcement learning, well, that's not supervised learning. So mirror descent guided policy search sort of plays this game where it tries to figure out what is the supervision that I can give to a supervised learning algorithm such that when it trains some complex policy, that policy will do the right thing. So it's like, if you know that only supervised learning is ever allowed to touch the neural net, what can you give to the supervised learning algorithm so that it does the right thing for solving a reinforcement learning problem? And the way that the algorithm works is something like this, that you're going to basically have a model-based teacher that's going to generate training data for your supervised learning algorithm. So that model-based teacher is it's a kind of model-based RL method, but it's not a deep model-based RL method. It's just you can think of it almost like a non-parametric algorithm. So it'll look at a few different trajectories that you took, figure out how to improve each of those individual trajectories by themselves without reasoning about any policies. And then that'll generate training data so that your neural network can be trained with supervised learning to do better. So instead of reinforcement learning, which looks at the parameters of your model and says, how do I change these parameters to be better? In this mirror descent guided policy search, it actually looks at the trajectories that you executed, fits a model, figures out how those trajectories should be improved, and then adds those improvements as training data for regular supervised learning. That way, the neural net is only ever trained with supervised learning and standard backprop.
Okay.
But at a very high level, the reason that this procedure is efficient has a lot to do with why model-based RL algorithms are efficient, because it really is a kind of model-based RL algorithm. It's just one that, under the hood, uses standard supervised learning to train the policy neural network.
Mm-hmm. So there's another interesting paper I came across, and that was the one on policy sketches.
Mm-hmm.
Can you talk a little bit about that work and what the goals are and what the results were?
Yeah, I'd be happy to talk about that. So that was work by a student named Jacob Andreas, together with Professor Dan Klein, who's another professor here at UC Berkeley. Jacob and Dan, they both work on natural language processing. So the premise in that paper is that we'd like to see how symbolic descriptions of tasks, you can think of these as very, very simplified natural language, how symbolic descriptions of tasks can be used to improve learning. And the key ingredient there is that we'd like to basically see how symbolic descriptions can improve learning without assuming that those symbolic descriptions are grounded. So without assuming that the agent already understands what the symbols mean. So if you, let's say, go to a foreign country, let's say you don't speak French and you go to France, and someone tells you in French how to, let's say, make a piece of furniture out of wood, and then they tell you how to make another piece of furniture out of wood, and then they tell you how to make a bench out of wood. Well, listening to those descriptions, you'll probably notice some common patterns. You'll probably notice that some words repeat, and if you hear enough of these descriptions and you actually perform those tasks and you kind of understand physically what it means, you'll find those patterns even if you don't actually speak the language. And eventually, when you hear new phrases describing new items that you can construct out of wood, for example, you might be able to put the pieces together and figure that out more quickly. So that was kind of the idea that we were working with. So what Jacob did is he constructed this sort of simplified version of the Minecraft video game. So it's like a little crafting video game. It was simplified because we didn't want to deal with vision. We just wanted to deal with kind of simple, kind of top-down navigation problems. And it had these tasks that were like, pick up the wood, or chop down the tree, pick up the wood, make the chest, for example. Chop down the tree, get the wood, make a boat, or grab the coal, put it in the oven, and so on. And there was a long list of these different tasks that the agent could perform that were constructed out of these symbolic verbs, essentially. And the agent would be given a set of these tasks, it would learn them, and the symbolic descriptions would just be given as an additional input. So they would result in some decomposition of the neural net, but there's actually different ways you could do that. But essentially they would be provided as an input to the agent without telling it what those symbols really mean. And just by learning the different tasks with the different symbolic descriptions, it could actually figure out how to then use new symbolic descriptions to solve new tasks more quickly.
Interesting. Yeah, it's funny when we talk about learning object detection in images, the amount of data that is required to train a neural network to figure out what an object represents seems so large compared to our ability as humans to do it. This is an example where I would need at least 1 million examples of the French sentence. So not knowing if I didn't know French, I can imagine needing a ton of examples of training examples for myself to be able to figure out the language and then how to put that together to make some furniture.
But if you spoke Spanish, you'd probably figure it out much more quickly. And that's
this is true.
And I think that actually that there's something to that as far as how the learning-based systems can work better. I talked before about multitask learning, and one of the things that distinguishes humans from these learned models is that humans are actually always doing multitask learning. We're always doing multiple things at once. We're looking for things in our environment, doing something. We're worrying about what we're going to have for dinner. We're worrying about some other stuff. We're observing some interesting, car that we see on the road over there. We're always doing many, many things. And perhaps a lot of our efficiency is actually down to this fact that we're never learning anything truly from scratch. Because we're learning so many things all at once, any new thing that we have to do, we get a broad basis of knowledge on which to draw to figure out that new thing. So in a sense, perhaps what we're doing is we're actually extremely broad kind of multitask learners, and maybe that's a big part of how we get that efficiency.
And what's the relationship between multitask and transfer learning?
Well, multitask learning is one of the ways to get transfer learning.
Right. So in multitask learning, we're learning multiple things in parallel. And in transfer learning, transfer learning is a broader idea that includes taking pre-trained models and using them, applying them to other things. I guess the direction that, the curiosity that has been piqued is like, how do we combine all of these things to, make our ability to train these models even faster?
Mm-hmm. Right. Well, so one of the things we've been looking at quite a bit actually is how we can use past experience to accelerate future learning. So that we've worked on this in the context of reinforcement learning, supervised learning, and so on. There are a number of ways you can approach that problem, but they all sort of boil down to some version of looking at your past experience, breaking it up into, little pieces of training data and little pieces of validation data, trying to build your model such that when it sees that little training data, it'll do well in that little validation data, and do this many, many, many times so that you get a model that's basically good at quickly adapting to small training sets. There are different ways that you can construct these types of models that, many other groups and us have looked at, but that's sort of the big picture setup. These are sometimes called meta-learning algorithms. I think that's actually an extremely promising direction for the future to really take deep learning methods beyond this regime of always relying on really gigantic data sets. And I think it goes hand in hand with multitask learning, that basically the way that we can get to the kind of efficiency that we see in humans is by solving many tasks, solving those tasks in a meta-learning context so that we're using our past experience of solving old tasks to accelerate the solving of new tasks. And then when we encounter new tasks that we hadn't seen before, we'll generalize and quickly adapt to them.
Mm-hmm. And does multitask learning necessarily imply a single network across all of the tasks, or are there variations there?
There are definitely variations. So one of the things that we've studied actually, as well as several other groups, is how we can construct actually modular networks. So networks that will have some components that are shared and some components that are distinct between tasks. And the nice thing when you build modular networks, actually the policy sketches paper you mentioned is an instance of this that also had modular networks. When you have modular networks, one of the things that you can observe is that there will actually be kind of interfaces that emerge naturally between different modules. So in a robotic context, let's say you might have a module for perception, and maybe you have one module for a color camera and a different module for LiDAR, and then you have a module for actuation for a robot with 4 links and a different module for actuation for a robot with 3 links. And you can mix and match any combination of these. So you can say, okay, here's a LiDAR robot with 4 links, here's a RGB camera robot with 3 links, train different combinations of these modules, and then you can actually find that you might get generalization to new combinations of sensors and robots, and you can figure out that bottleneck between the two modules actually constitutes a kind of a learned interface. Because different modules, they have to basically adopt a common interface because they don't know who's going to be downstream from them or who's going to be upstream.
And at the systems level, what are the implications of that? Is it then easy to take one of these modules and drop it into another system, or does it not quite work like that?
Well, I think that's part of the hope. So I think we haven't seen that yet, but in the long run, that's, I think, one of the really interesting things about modular network designs is that perhaps it could actually be possible to use this as a way to combine the benefit of end-to-end learning with the benefit of modularity to be able to actually, train up some component. Let's say if you're doing autonomous driving, you train up a particular vision component on one car, maybe supplement it with ImageNet data, and you just drop it into a different car. But then that different car has its own modules for, let's say, controlling the acceleration or something like that. So I think that's part of the hope. We're not quite there yet. This work is still in fairly early stages, but I think that's definitely a really exciting place that this kind of stuff could go.
The scenarios you just described were all end-to-end trained, at least in an initial system. They're end-to-end trained as opposed to training a module at a time. Is that right?
Right. So that's actually that's the nice thing about modular neural networks as opposed to modular anything else, is that neural networks can be composed. So if you have a modular neural network, you can still train the whole thing, a combination of multiple modules end to end. Now, when I say end to end, there could be different ends. So end to end could mean that your vision system is simultaneously trained on ImageNet recognition and feeding the right visual representation to a downstream control module to perform some task.
Yeah, it's interesting. So The general question that I want to get at here is, I think the basis that you've laid out for end-to-end robotic learning makes a ton of sense. At the same time, when I talk to folks in industry about how they're using neural networks and deep learning, and I present this vision of, hey, we're just going to have this one Uber neural network that can figure everything out, invariably I get back some reaction that's like, no, we don't do it like that at all. It doesn't work. It's too hard. How do you account for the gap there? Do you see similar things, I guess, for one, and how do you account for that gap?
Well, I think one way to look at it is it's a little bit like the difference between gasoline cars and electric cars. So it's very difficult to, right now, or maybe even like 5 years ago, to make the case that, well, everybody should have electric cars because, well, gasoline cars are really good. Like, we've been designing them and improving them for almost a century. So, of course, you build the first electric car, it's not going to be as nice as a gasoline car that's benefiting from all those decades of engineering. But I think the technology is progressing. So I think the reason that you hear, especially, certainly in robotics, like we get this a lot, that you'd like to be able to use something like a manually designed motion planner on top of your learned computer vision system, because that motion planner is really good. Like, it's benefited from decades of development. So that's, I think, maybe the explanation. Now, the solution, I'm not sure. I think there are a couple of possible solutions. One solution is that, well, maybe we should see what makes that really nice manually designed component work so well. Can we incorporate that into a learning system? Or can we use it as part of an end-to-end system? So can we use that manually designed, let's say, controller, differentiate through it, compute gradients, and use those to improve our vision system? Or maybe we just need to make a little more progress in reinforcement learning to the point where we can replace that component without a loss of capability.
Right. Great. Are there any other things that you wanted to cover?
No, I think that's everything on my end.
Fantastic. Well, what's the best way for our folks to catch up with you, to learn more about what you're up to? I know you've got a webpage on the Berkeley site that will include a link to in the show notes. Are there any other ways for folks that you'd like folks to get in touch with you?
I think my website is a good place to start. Also, for anybody who's interested in learning about deep reinforcement learning, we do have a course that I and Chelsea and our colleague John Schulman taught at UC Berkeley, and all that material is online. So if you search for Berkeley Deep Reinforcement Learning course, you can find all those lectures. That can also be a good resource. But yeah, for getting in touch with me, definitely my website would be a place to start.
Fantastic. Well, I'll make sure to include a link to the course in the show notes as well. And thank you so much for being on the show.
Thank you.
Thanks, Sergey. All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. For the notes for this episode, to ask any questions, or to let us know how you like the show, leave a comment on the show notes page at twimlai.com/talk/37. For more information on industrial AI, my report on the topic, or the Industrial AI podcast series, visit twimlai.com/industrialai. The report is complete and it's beautiful, and I'll be notifying folks who sign up at that page how they can receive a copy of it shortly. Once you're done with this show, take 30 seconds to head over to twimlai.com/AISF to enter our giveaway for a free ticket to the AI conference in San Francisco in September. You could be one of 2 lucky winners. Thanks again for listening, and catch you next time.